ado, I'd like to introduce everyone to our IEEE Power Energy Society's webinar today entitled Converter Control Design Principles for Inverter-Based Resources. Our presenter today is Professor Lingling Fan of University of South Florida. So without any further ado, I'll go ahead and I'll turn it over to you, Professor. Thank you, everyone.
Okay, I'm sharing my screen now.
Yes, I see.
All right.
Yep.
Okay, going to get started. Thanks everyone for joining this webinar, spend time with me. So the title of today's webinar will be Converter Control Design Principles for Inverter-Based Resources. We will call it IBRs. And I'm the speaker, and I also have a collaborator, Professor Zishimil, online as well. And let me just go over to the agenda today. So today I want to share with everybody the history of vector control, the philosophy that used predominantly in the current day IBRs. And then we will start to talk about, because vector control is for motor drives, we will talk about the requirements for grid operation, how this vector control is adopted in IBRs. And the name of this control is called grid following. And afterwards, then we will say, okay, what are the real world operation concerns of this type of IBR? So we will show a couple of examples. And then moving forward, we will do this grid forming control design principles, which with the goal to tackle these concerns. So finally, we do a couple of comparison of performance of those different control philosophies in power grids. And then we will wrap up. So Latoya, do I have sound? Some people said there's no sound.
You do have sound.
Great.
So
All right.
you can continue and I'll help those folks try to resolve, but you do have sound.
Thank you. All right, so we will move forward to the learning objectives. So hopefully after today's talk, people will know the history or origin of the vector control and understand the basic requirements of the IBRs, and maybe get familiar with 3 units of the grid following control that we will talk about today, and at least understand how to do the synchronization, which is very important for grid operation using 2 methods, and then understand the challenges of weaker grid operation, and finally learn the principles of grid forming control. So these are the 6 learning objectives. All right, so now I move on to the first one called History of Vector Control. So actually, this is related to motor drives. So if you do currently, you don't do Google, right? You do ChatGPT talk. So I told the ChatGPT, please give me a brief history of vector control used in motor drives. So then it will start, give you a couple pages. So the first one is page, it says pre-1970s, it's the era of scalar control era. So if you take a look at the page, it says scalar control, VF control. So keep a V and F constant, sort of like keep the flux constant using in motor drive. So this is again an inverter drive a motor. So we don't see this one because this is all ChatGPT figures. I just copy paste that. On the other hand, let's move on to the second one. It is in about early 1970s. That's the birth of vector control. So the second figure, actually, I think ChatGPT pulled the US patent, not the US patent, the patent filed by Felix Bloschik in 1971. So I double checked that Felix Bloschik, he's engineer from Siemens. And in fact, another book, Control of Electric Drives from Germany, Professor Werner Leonard, and that book's original version was published in 1974. So we can just connect the timeline in the early 1970s. That's the birth of vector control. So what is vector control? Highlighted here. So if we have currents, stator currents 3-phase, we view it as a space vector, rotating space vector. And it can be decomposed into DQ frame, and one of the components aligned with flux is called the D component. Another is quadratic. So the D component is used to control flux. The Q component is used to control torque. So this is the idea. So if you look at the structure, it looks quite similar like today's IBR controller. Some level of similarity. So I use one line summary from, this is again from ChatGPT. It says, field-oriented control. That means vector control is a control breakthrough from the 1970s, whose real impact only emerged as inverter technology that include devices, pulse width modulation, the switching technology, plus computation caught up over the next 50 years. And of course, I give him lots of hints to say something like this. But on the other hand, if we take a look at 1991, Professor Leonhardt published a paper says 30 years space vector, 20 years field orientation, 10 years of DSP. So this is again 1991. So now today, we can say this, 2026, 65 years space vector, 55 years of vector control, 45 years DSP, now 3 years GPT. Okay, so this is again some kind of history, 65 years of space. We will talk about that one. Let me just go to the next agenda item. So now we will move to GFL, grid following converter control. So first, let's look at IBR. So there are lots of IBRs connected to grid. So I'll tell you, I have to again ask you whether the audio is okay. A lot of people says there's no audio.
The audio is fine. If it's not, I will let you know. I can hear
Excellent,
you
excellent,
loud and
excellent.
clear.
Yeah,
Yeah,
and you're a
I
little
hear
bit
you loud and
nervous.
clear. No
All right.
problem. No,
Okay.
I hear you loud and clear.
Excellent. So let's move on to look at an IBR, inverter-based resources. The DC side could be just the solar, just the wind, type 4 wind, and a battery. And we all use those type of thing called inverter interface to connect to the grid. And so look at that. This is the Chuka filter, and this is the point of common coupling, and that's the grid. Now, what do we do? Let's think about if you want to attach something to the grid, what do you need? We need it to be synchronized to the AC grid because it's AC. You cannot just switch it and like make this just sinusoidal or any, for example, just make the 60 hertz sinusoidal waveform. It may not be working because the grid frequency is varying. Right? Second, the inverters are very vulnerable to overcurrent. So that's why we require tight current regulation called current control. After these things can be happening, like you can interconnect to the grid, you can very well regulate your current. The next thing is now you can provide desired real and reactive power for a battery, right? And on top of that, you can also provide voltage control, voltage regulation, and frequency support, some additional stuff. So now all these things should be realized by control units. What are they, right? So first of all, it's a synchronizing unit. It can be power-based, it can be voltage-based. In fact, if you think about this in synchronous generator, it is power-based. And then the current control unit, that you have to be make sure the tight current controller. So finally, the PQ regulation. So you can see this is sort of like already we show 3 units. Now, where's the vector unit? Vector control. So how we connect the PQ regulation to current, that is vector control. This idea is very similar to the motor drives flux-oriented control. On the other hand, this is voltage-oriented control. So let's explain this one first. So now we are going to looking at vector control in the IBR. So imagine that we can treat an IBR as a current source and attach it to a grid. And now we want to regulate the P and Q. So what should we do? We trying to make sure that the current is aligned, or the current component called DX is aligned with the voltage component, right? So there's a voltage. So we decompose current into 2 components. One is aligned with voltage, one is orthogonal to the voltage. So the aligned voltage called dx is generated P, the other one generated Q. Right? So that's the idea. If you think about it, one is flux, one is torque. Right? Now it's just changed. It's P and Q. So basically, it's easy to understand. P is generated by the voltage and the current component that is aligned with the voltage. And this voltage is PCC voltage or POI voltage, point of interconnection. But the Q is generated by the voltage and the current component, Q-axis components. So that's the idea. Now, what is the requirement? The requirement that you have to be able to set up a frame, and that frame has to be aligned with this POI, that voltage. So DQ frame has to be aligned with your voltage frame. So that's the idea. So on the other hand, once you realize this kind of alignment, you have the DQ component ready, and the controller can be easily realized by feedback control. Just pay attention, because Q is a negative voltage multiplied IQ, so you have to use negative feedback control, sort of like you have put a negative. This is a or just a traditional negative feedback, but this one, if you do reference minus order, that's a negative. All right, so now we explain this sort of like a PQ controller once you have the DQ component ready. So then the next question, how can I really generate a frame that align to the voltage? So the first thing we have to understand, the voltage have an angle, which is rotating. And if it is actually just in the time domain, it's cosine and sine. So for example, the voltage is cosine omega t or sine omega t and plus some angle. So how do we get this angle? Well, this is like a rampant angle. So it's a very much easier to do it using e to j omega t, right? E to j omega instead of just cosine and sine. So if you have three phase, use the clock transform. Actually, you can just get this rotating space vector in the x, y like space, right? So look at that. Omega t is changing, and its ramping signal is keep rotating. So this is the nice thing about the space vector to date, 65 years. Although the original clock transform is not in this format, it's the real and the imaginary alpha beta, but you combine them together. Now it is really nice rotating space vector using three phase. So in this case, now we have the angle explicit to us, right? So now we wanted to measure an angle to measure this ramp signal. So what do we do next? Park transformation. So first, we are going to set up DQ frame. From, of course, ABC to DQ is called park. But let's just looking at it. Suppose I set up a DQ frame, D is the green, Q is the purple, and the rotating speed with the voltage vector is the same. So now I get two components, which is constant values. And we love constant variables because we can use PI controller to do everything to handle that. On the other hand, I really wanted this blue one, the green one, align with the orange one. And now how do we do that? That we have to really make the tracking happening, do some kind of feedback control. So for example, I'm trying to make this Q, this orange align with this green line, right? That's aligned. Once it's aligned, what will happen? Look at the VQ component, the projection on the Q axis. The projection on the Q axis is actually in the purple, right? It will go to zero. Once you do alignment, it will go to zero if you look at that, right? So the ultimate goal is just to make sure that the VQ go to zero. So, and we use this concept again in control design. And the principle of PLL, phase locked loop, is just to do this couple of things. Number one, do clock transform, do a space vector. Number two, convert to DQ frame. Number three, make the Q component go to zero. How do you make it to go to zero? Just do feedback control and use the PI controller enforced to be zero. So since we have a ramp signal, we have to have two integrators. We want to get a frequency, we want to get an angle. So now we are done with the first step called synchronization. Okay, so the next, let's look at the overall control structure, because we have already see how you control PQ, how you do sync. The internal one of the current control, we may not talk too much about it. So, but let's look at, first of all, we have two sensors, measure the current and the voltage. And those are all three-phase instantaneous sinusoidal waveforms. And after that, PLL, it's called voltage-based sync. phase locked loop to generate an angle, which is called a synchronous frame or whatever it is, sync angle. Using this angle, the voltage and the current will be transformed into DQ components. At the steady state, they will be constant. Now we are going to use this IDIQ because the constant value, we can just do very tight current control, right? And this is tracking the reference. And who's generating these references? P and Q. Here I put P and V, but it can be P and Q as well. And internally, you can put a current limiting unit just to make sure that all these references will be kept. So then your converter will not be over current. So that's a very nice DQ frame control of the GFL. So if we put system into a model and just using 3 blocks or the DQ transform, this is done in MATLAB Simscape. Let's look at what will happen. Just looking at T equals 1 P reference step change, right? So what do you expect it to be happen? Because P reference change, if we go back to the previous control block and also shown here, the current reference, right? So P reference change, the first thing, the PI controller will kick off, and then the current, DX current, real current will improve, and the current will track its reference quickly. Once the current improve, real current improve, what will happen next? In fact, the grid will start to kick off because you will see the VD voltage is starting to decrease. On the other hand, QX is trying to make it zero. You have the PLL make this guy zero. But the voltage start to decrease because we are using PV controller, voltage controller, so the Q-axis current will also change, trying to decrease. So you inject more reactive power to the grid, and the purpose is just trying to make the voltage going back to 1 per unit, the original value. So this is the thing that is happening when you design the control and some references changing. So we will not talk about too much on this thing, but just showing that the PQ control or PV control, anything that design, you can realize the control function very well. Now you put into the grid, what will happen? It works pretty good if your grid is nice. On the other hand, there are later on, after you put enough, a lot of IBRs into, for example, Australia, into Texas, then you see something happening. This is called real world operating challenges that will happen. So very much, if you want to take a look, it is in 2017, NERC, North American Electric Reliability Corporation, published a paper called Reliability Guideline, integrating IBR into low short circuit strength system. What is this? Weak grid. Weak grid means what? Weak grid means just the transmission line is pretty long, and the 7 equivalent impedance is very large. So now first, they identify in chapter 2 of this white paper or this guideline, they identify 3 concerns. First concern is classical voltage stability. Second concern is control interaction and control instability. So later on, I checked this, I was showing you, these 2 are actually very similar. They are all related to the voltage stability, but I called the second one using different color, I called dynamic voltage stability. And the third one I mentioned is the PLL-related stability called disturbance write-through capability. Although there are no real-world events, but we'll put one and show today. So let's look at the 2 real-world field measurement data from the report. So the first one is from BPI. It shows a wind farm. Basically, you ramp up real power and the voltage is going down. So this is sort of like very classical voltage stability because you don't like this one, keep sending power to the grid and the voltage going down, and we understand this part. And then the second one is from electronics, and that is sort of like a simulation results from PSCAD. I think what happens is they reduce or increase the grid impedance, reduce the SCR short circuit ratio, increase the grid impedance, and then you see 7 Hz oscillation come up from the power, reactive power, and the voltage. And noted this IBR sort of like in the voltage control mode because you can see that the voltage is not changing, right? But the reactive power is sort of like increasing. And you have weak grid, you want to keep a voltage same, you have to increase the reactive power. And so these are the two things, but I wanted to show later on. These two is just in simulation, you can also replicate a lot of them. But first, let me just show these two. So now let's try to understand these two, how these two are happening. So if you just take off the PQ controller, the outer control, have the synchronizing unit PLL there, have the inner current control there. So now we're doing experiment. The experiment is just to ramp up the current, real current, not the reactive. Reactive current will keep it to zero, Q axis. So what will happen? If you ramp up the ID, the voltage is going to drop, the PCC bus voltage, inverter voltage drop, the angle keep increasing, the sync angle is keeping increasing, and the power is having a theoretical limit and then going down. So this is experiment is done at the weaker grid condition. Xg is 0.75. So theoretically, the limit, if we do calculation, is limited to 0.66, something like this. Okay. So now the conclusion that we draw from here is we can see that the increase in the real current, ID is dx is current, but it generates a real power, so we call it real current, leads to an increase in angle, synchronizing angle, and reduction in voltage. So that's a characteristic that we found. So with this characteristic, let's looking at the PQ control versus PB control. So we don't change P control, but we change either it's reactive power regulation, or you trying to make the voltage constant. So if you do Q control, this is what happened. You trip a line for in PSCAD. This is the EMT simulation. You trip a line, make it grid weak. The first one is just showing, yes, the voltage is going to collapse, right? So then the next thing is, if you do voltage control, then we see oscillations, right? So that's the difference between classical voltage stability and oscillatory voltage stability. So, but I think these are all related to the voltage stability. All right, so now we are going to do the second event or from the another report. This report is from Texas 2021. It's from NERC, and it's describing the Texas event, Odessa event disturbance. So what is happening here is we see a lot of PLL, loss of synchronism, and large-scale PLL tripping. So one cause is called the PLL, loss of sync. And it has the solar PV tripped about like 389 megawatt. I put a remote here because this is my annotation. Just say these solar PV farms are very remote to the fault location. So let's take a look of the map. So the fault location is about maybe the red dots. And then the PVs that are tripping in here actually have this PLL, loss of sync tripping is in blue dots 200 miles away. So it's a very strange to everybody. It's sort of like, yeah, why the PV that is close to the fault are not having the issue called PLL, loss of sync. So why is that? So let's do another experiment. So another experiment, if you do EMT simulation, you can see this one. It is that you put a fault, the grid voltage dip. This is again a weaker grid. You can either make the grid voltage dip, or you can put a fault at the IBR close location. So if you put a grid voltage dip, the IBR voltage is not too much dip. On the other hand, if we look at the angle and frequency, the synchronizing angle, the PLL's frequency, what happens in the two cases? Look at that. The first one says if the fault is remote, we have frequency jump to 64 hertz. On the other hand, if the fault is close, the angle, the frequency is jump to 61.5 hertz. And of course, the angle is like remote fault is worse. So this is very much against our common sense regarding the synchronous generator. In synchronous generator, if you have fault close to generator, of course it is worse. So GFL is more vulnerable to a remote fault. That is actually what we found. And we did a paper to show why is that. Basically, you can use a phasor diagram to document the mechanism, the large angle deviation. So a couple of things happening is that, first of all, you have to have a weaker grid and you have to have high transportation. And then the voltage at PCC bus, inverter bus, and the grid, you have an angle, significant angle. On the other hand, treat the converter as a current source. So the current source, DQ, ID, IQ, they all have voltage drop across the transmission line. Now, the current source, the current will not jump immediately when you have very significant jump, dip of the grid voltage. So let's look at from the grid voltage and dip to VG prime, the current vector or the voltage drop will not change. Then your PCC bus voltage, inverter bus is basically have very quick jump, delta Q, very significant. So that explains the sense. So this is again related to the power exporting level and the grid strength. If the grid is strong, if the power exporting level is small, lower, then your original theta is not that large, you cannot see that. And we did a couple experiments just to see what will happen. So the PLL gain will be related, right? So if you have a large gain of PLL, you may jump a little bit more compared the blue and the red. And then, but if you have power reduced, then your jump is much smaller. It's just a 60.7 hertz in all these comparisons. So anyhow, that is some kind of explanation of the GFL. That's its characteristic based on design. It just behaves this way. So as a summary, if we look at the reports from NERC from starting from 2017 to like 2022 or even like I think the recent one, right? So look at that. The concerns are voltage stability. And this can be done just to improve the voltage control. For example, instead of doing Q control, you do QV control or do additional voltage regulation. On the other hand, the D-axis auto control is really troublesome, right? Because P generator current, right? Using P generator current, you found it. If you have a low voltage, you have a low power, leads to more real current injection. More real current injection leads to more lower voltage. So that's some kind of thing pretty not desired. What about low voltage right-through? Another thing is this kind of thing called low voltage. You have a fault and the remote grid is weak. So this sudden grid voltage dip leads to the voltage angle jump immediately. PLL follows up. Then PLL also shows large jump. Then the next kickoff is that the low voltage leads to reduce the real power, increase the real current. And then again, in the grid side, an increase in ID exacerbates the voltage dip and the angle increase. So if you think about this, it's just looking at the weaker grid operation, low voltage right through. It is challenging because you have this coupled voltage stability and synchronizing stability issue together. So that becomes challenging. Okay, so this is the second part of this talk. Now we are start to brainstorming and do the grid forming. So the first thing we ask ourselves, how to mitigate IBR with grid operational challenge, because you said that these are challenging. How do we change controllers? So a couple of things that we think about, yeah, because PLL is sort of like you follow the angle too much, so probably we should change PLL. We don't want it to be so sensitive to the voltage. So in this case, we probably can change PLL. The second one is this outer control loop of the D-axis. When you have P2 ID reference, this logic is really also another issue, right? So anyhow, when we go to the GFM design, let's think about this couple of things that we will talk about. So let's now move to the main topic of today is the GFM design, grid forming design. So in the literature, if you replace a PLL by a power-based synchronizing unit, then it seems like people just call those GFM. So let's evaluate a couple of design principles. So the philosophy is that the GFL design has been there for decades, works very robustly. People have benefited a lot, and we don't actually want very radical change of everything. In addition, in particular, the current control is really nice. You can just explicitly regulate the current and push a limit there. If you change everything to be voltage, how do you apply this? So it's very difficult to that. So the once structure that we discussed today, we're all having this inner current control loop there intact. All right, so let's look at this one. This is again a grid following control that has 3 units, right? Outer control, inner current, and the phase lock the sink. So let's do the first car. The first one is, instead of using voltage, now we are going to using power. So power reference minus power and do a dribble control, generate the angle. A lot of people using that, or you can just do some kind of variation, do some virtual synchronous machine control using swing dynamics. But in the end, it is all having power as input to have a generated angle. So now this is replaced. Then we are going to change the outer loop, all right? So let's examine what is PLL actually is doing. PLL helps us to generate an angle for synchronization. But on the other hand, it also is doing another job called frame alignment. Align your synchronous frame, DQ frame, with the PCC bus voltage, with the voltage that you measured. Right? So in the next one, when we replace it to be a power control, it's generated angle, good, same theta. It is also doing power regulation, but there's no frame alignment. So the power regulation is here. So we don't need to do it again in the outer loop, but we have to have the frame alignment done in the outer loop. So therefore, it can be easily see that frame alignment has to be in the outer loop. And in addition, we have to do voltage control or reactive power control in the outer loop. This function will be there. So that's the change from the outer loop. So the conventional design of IBR, of GFM, actually have been popularly used in the literature, actually achieve this function. So let's look at design one. Now, I put it as Imperial College, and I think people have seen this type of design in across academic literature. A lot of the papers books are using this type of structure. So the original paper I searched is coming is from in the Tim Green, who's the head of the Imperial College ECE department, and his 2007 paper actually is a DQ frame and grid forming, this type of thing, the power droop. So let's take a look from this design. First, replace the PLL by a power synchronizing loop, and the next one is to achieve the frame alignment. So again, frame alignment is to make a VQ 0, right? And then voltage control, you copy it here. On the other hand, he's doing D and Q like this. So I call it as coupled voltage control in the magazine paper, we call it. And this structure, again, like I said, you see it everywhere. I think I first saw it in the green book done by Professor Yasani and Iravani, and they have green book published in 2010. And then I found in the literature, a lot of people are using that. So what is the philosophy of this one? Because look at that, there is like another sensor, right? And there's a capacitor. So on the next page, I just talk about the philosophy of this design, and that you can find it from the textbook as well. So the philosophy of design is, yes, you want to regulate the voltage, right? Regulate the voltage, basically make a VD follow an order VQ equals 0. So essentially just regulatable. You have to have a Planck model. So the Planck model that the 2000 paper that choosing is the capacitor voltage. So in the capacitor voltage, it's like this. You can regulate the current, right? Actually the current difference. So in the DQ frame, you can regulate, you can write in the J omega, take it out, sort of like cross coupling. So let's do a Planck model. The Planck model now looking at this ID IQ related to VD and VQ like this. So you look at that, there is this another current. You have to really measure another current to get this. On the other hand, when you design controller, you really like just this UD to VD and UQ to VQ because it's decoupled and it's just 1 over CS. So in the design philosophy, it is just to measure the VD, the feedback, and change the VQ, UQ. So that's it. But you add additional stuff to generate this current, the converter current, right? So that's the design philosophy. Is you are using PI controller generated UD using UQ. On the other hand, UD have to add this compensation called cross coupling unit to make sure that you are finally generate ID. But in this case, it's ID star that is done. So to summarize, the controller is trying to track the VDVQ reference, but he's using the capacitor dynamics. The requirements on the sensors, instead of previously we used 2, now you use 3 sensors. The auto control bandwidth, this design, there's no consensus in the literature. I checked a couple of them. Sometimes people use 70 Hertz, sometimes it can go 200 Hertz. And then another thing, let's check. The DX logic shows that the voltage dip leads to an increase in current. Look at that. If we have voltage dip, then the current again will increase. So, and actually in the grid operation, like I said, this is not that desired in the weaker grid. All right, so let's move on to the brainstorming. Again, brainstorming. So when we read this literature, we are power system guys. So we said, what if there are no shunt capacitor? Or what if we put a shunt capacitor far away in the POI in a high voltage level? Then where's the sensor? How do I put the sensor? So the thing is that let's revisit this design and let's replace again PLL to the power level control. But on the other hand, we do the same thing, use different structure called decoupled voltage control. So the concept is that we don't want to change the D-axis, Q-axis, because this looks fine. Why do you need to change that? On the other hand, look at the Q-axis, D-axis control. Now, previous is real power. Now we change it to be alignment, to do frame alignment. And why is that? Because you make a VQ 0, you are sort of like changing angle. In the VQ itself, it is reflected to the angle. So in the D-axis, in fact, ID is now reflected to angle. And ID power, so this is all the real power part is done. So now you look at this part, it's very similar like the PQ vector control, except that they changed the only thing is that they changed the D-axis. So that's why we again call it the vector control in this case. So this one, once we designed, we checked the literature, I found nobody else has found it, designed that. So we filed the patents, we did the hardware, we published a paper. And it has been implemented in the hardware in national instrument, and you can see it here, and tested in the hardware test bed. And we can put the GFL, GFM together because this one is very easy to do co-design. And you can share lots of components here, and you can do control switching, and then you do grid islanding, grid reconnecting. Everything works super, super nice. Okay, so that's the design of vector control. So now move on. Also check the literature in the industry. In the industry, in 2024, there's a different design called virtual admittance control. So this is done by NIDEC. And the paper is from SIGRI 2024. So the first 6 authors are from NIDEC. That's why I call it NIDEC. So in the paper, magazine paper, we had a typo. We call it NIDEC. So actually it's a NIDEC. So the philosophy I'm showing you here, trying to use the voltage current measurements. You measure those, and then you are saying, okay, I want this inverter to look like a voltage source behind impedance. How can I realize from the controller? So easy. You write it in the static frame of the equations. Right? You change it to the DQ frame. You separate the D and the Q. So that's it. You convert this equation into the blocks. The only thing you need to pay attention is that the current, you generate the current, but on the other hand, I'm using current reference because you don't want to touch the inner control. It's super fast. The current reference order is same as the current measurement. So this one, you can just looking at that, yeah, you do the voltage, right? In the voltage compared to the PCC bus voltage, have an error, but make sure that you have the coupling part here, and then pass through a IL filter, then you generate the current. Right? So this one is called virtual admittance and works again super nice. You can implement in the control block and everything is together, 3 units together. So next we want to do is the next chapter. Now we have different parts of the control philosophy done. Let's look at their performance, right? So the performance is sort of like, first we compare weaker grid, low voltage right through, again, have a grid voltage drop and test it. So we compare actually 4 types of converter. One is the GFL that we showed that. The second one is the Imperial College one. And the third one is the USF one, decoupled one. Then another one is this virtual admittance control. So all those are trying to make the control objective similar. For example, if we try to regulate the voltage to be 1, then rest is also trying to regulate the voltage to be 1. Right? So, and then this is ABCD that we did. Let's look at the low voltage right through. So grid strength is short circuit ratio at 2. So you put the impedance there, and then you have 75% grid voltage dip. So what will happen for the GFL? the system is losing stability because the angle keep increasing as the voltage dip, then VQ is increasing, VQ is here increasing, then the frequency increasing, the angle is keeping increasing, and finally they lose stability. And then look at the coupled voltage grid, it's also losing stability as well, although it's slightly better. And let's look at ID, the real current. Both of them have the real current increase, which is not desired. Right? Let's look at the other two. The other two is basically they can ride through, very nice, and the real current is reducing once you have the the low voltage dip. Right? So the design, this is based on design philosophy. You can just achieve this kind of function. That's nice. Right? So that's the first test. The second test will be, what about series compensation line? So because in Texas, you have series compensation line, and in Chile, you also have series compensation. That's pretty common in Finland, right? So let's do experiment. So initially, the inverter, IBR is connected to a parallel line, then afterwards, triple line, make it a radio connection. So A and B showing that, oh yeah, no issue, everything is working fine. It's a 50% compensation line, and everything is working fine. And C and D, the coupled control works fine, but the virtual admittance behave like a voltage source. Now it shows 28 Hertz oscillations. And in the paper, we also provide why is that? Because the other three, you can view it as current sources. But this one is very distinct. It is looking at the voltage source. So if you have voltage source connect to an impedance, ILC impedance to the grid, and you can figure out why that you have P and angle. So the power frequency droop can be modeled just like this: is delta P, generate an angle, generate a frequency, then generate an angle. But the angle is from the voltage source, and this voltage source is the angle actually can also influence through the grid, influence the real power. Right? So because you have RLC circuit, this guy called the imaginary part of your DQ frame admittance is very different from the non-compensated one. So for example, let's look at the blue line is the non-compensated one. You have a peak at about here. But after you put compensation, you can see the peak is moved to the subsynchronous range, and the higher then you move down. In addition, it introduces a phase lag, and we don't like a phase lag actually. So now if we put the entire thing as a loop again, that's what happens, that you can clearly see in 75 Hertz, probably there is this kind of oscillation at 10 Hertz risk. In 50%, then it is probably have 20 Hertz oscillation risk. On the other hand, that the last page we show 28 Hertz, why is that? Yeah, probably this one is going here, right? Because we have virtual impedance. I didn't model there, although this is 50%, but if you include the virtual impedance, then the compensation level is less. No? So the numerical study has not been explicitly to match that one yet, but this at least explain why is that the voltage source. So to wrap up the major takeaway that if we compare 4 of them, we can ignore the middle part, because middle part is GFL at the plant level or at the frequency control. It's going to do the work, but you have some coordination that you have to pay attention. If we check those weak grid, low voltage rise through, the 2 inverters, 2 design, GF design is good, very good. But series compensation, the virtual admittance behave like voltage, so then you have an issue like this. So there's a pro and a con for each, but the one called vector control that designed by USF looks like pass through all the tests here. At least 2 tests here that we have to continue to do all the tests. So as the wrap up, so let's look at the learning objective today. So for example, first we claim that we want to know the origin of vector control. So I designed a couple of quiz questions. GFL is similar to vector control in which applications? Yeah, motor drives after today. So, but what are the key differences? The differences, in fact, we just talk about torque and flux become like real power and reactive power. Additionally, there's synchronized unit. In motor drive control, you do standalone. Here you have a grid, right? So there's a synchronized unit. So that is related to how you generate the angles. And in motor drive, I think how you generate the angle is also a big challenge. In grid, this is using PLL and power. So, and that's the technique that we use. The basic requirements of converter control design for grid operation. Understand that part. What are the basic requirements? People usually ignore that part. Synchronizing is the critical part. And after that, then you do, you limit the current. And then you have this peak regulation, frequency, voltage support. So I put one quiz question here. Which one is more difficult, synchronize to a DC grid or AC grid? Yeah, DC grid, you don't have to do anything too much. Right? AC grid, there's an angle. That angle, you have to measure that, synchronize that, generate an angle. DC grid, you can just directly put this together, right? As long as the voltage is similar. Then let's get familiar with the 3 units of GFL. What are they? The 3 units we talk about is basically sync unit, control, inner current control, then outer power control. I hope that people also understand there are multiple ways to realize synchronization: voltage-based, called phase locked loop, or power-based, sort of like a synchronous generator. The challenge of weak grid operation, dominant challenge is the coupled voltage stability and synchronized stability issue in the weak grid. That's weak grid. Let's have some level of familiarity of different design principle of GFM, so at least you can see a couple of designs. Today we showed, right? Once you replace PLL to a power-based synchronizing in the outer loop, you have to design differently. It can be either emulate a voltage source, or you can do some kind of voltage control frame alignment. That depends on your design goal. So that's this one. And if you like further information, we have a couple of books published and a couple of papers there. So let me just talk about this couple of books. The first book was published in 2023 by CRC Press. And why do you have to read books? Because you said, okay, if papers, talks are very good, the magazine paper is especially good to read. Those papers, magazine papers, and talks, we don't give numbers, right? If you really want to replicate something, there are numbers. So this paper specifically says we care about the numbers, very important. The second paper is following up the first paper, but specifically focused on weak grid integration. So we talk about like compensation, series compensation, what will happen. Also talk about the fault analysis, the protection part. So let's move on that direction. So both books are written for practical practitioners. So if you look at the first one, Dr. Mohammed is a manager in IESO Canada, and he likes the first book very much because he thinks this is very, very good for his team. And the second book was read by UK from Scotland, and both of course, they are engineers, and they have read the book and found it's pretty insightful, lots of examples. Okay, I think we will leave much of the time now for questions, and let me just see if I stop sharing, I can see the question, or maybe Latoya, you can read the question to me. So it looks like I'm not able to see some of the questions.
Okay, thank you. Thank you for a great presentation. Yes, so we do have a few questions in. One of them is how much is the failure of GFM attributed to poor control design rather than the structure itself?
Somehow I couldn't see the chat box, so I don't know where it is now. Yeah, so design, this is ongoing, so we couldn't say too much about this. This is the ongoing pilot not an ongoing pilot. GFM research is still ongoing. So to date, then we cannot reach a lot of conclusions, right? Because you have to put in operation, make it operate for a decade, and you accumulate lots of experiences. Yeah, so it's pretty general. So yeah, we can move on to the next one.
Sure. Okay. How can we overcome the slower response of QV loop?
Slow response. That really depends on, you can design it faster, you can design slower, but the important thing is that your design is like this. You don't want to mess up with inner current control. So I think people usually design it in the 10 hertz region, right? Bandwidth of 10 hertz region. So I don't think this is a very big issue unless you are talking about the power plant level control and there's delay. Inverter level, I think people can just make an inverter behave like a voltage source. It should be okay, right?
Okay. How are SSOs different from the interconverter oscillations? Are they same or different?
Depends on how you say SSO, because SSO just means subsynchronous oscillations. It means a phenomena, right? It's not have anything to do with the mechanism. So when we say something, sometimes we say something that includes the mechanism already. For example, SSR, subsynchronous resonance. People usually refer it to be, oh, you have a capacitor, right? Series capacitor, then you call it SSR. So if we talk about, well, so maybe the question is about, well, whether this one is grid level. When you connect to the grid, you see this, or it's just you don't connect grid is very strong, then you put these two together, you have this. So one is design issue, right? You have the power plant, you should design it to be working pretty well, unless your grid operation becomes challenging, like a weak grid, then you see issue. Then you have to differentiate between the plant level issue versus the system level issue. Yeah.
Okay. How do you decide on current limiter values in different configurations?
Can you say it again? How do you?
Decide on
Mm.
current limiter values in
Mm.
different configurations.
In different configuration. Current limit, you can put it very simple, just to okay, make sure that the current magnitude does not exceed a certain level. But of course, in the real world operation, then you have lots and lots of options to do that. Sometimes it's Q priority, P priority. Well, whether we want to do the reactive power first, the reactive current first, the real current first. So lots of options. So for this, we don't cover that, but people can refer to all these industrial documents like WAC modeling. There are lots and lots of options. You have lots of selection options to choose as well. Yeah.
And what about the nonlinear control techniques to improve the GFL capability?
Yeah, I think people always have this obsession to do something nonlinear. But what we are talking about is the nonlinear controller, right? The entire system is nonlinear. And we did all those type of things called DQ, ABC to DQ to make it look like linear, right? Then we apply things, and everything that we do, it's nonlinear, like a PLL, it's nonlinear. So I usually have this question: what are you talking about exactly? Let's find out exactly. Otherwise, it becomes just a very general talk, right? It's general, very general. You cannot have answer, or you don't know what is the question. Okay, let's move on to the next.
Okay. What about the transients during GFL to GFM mode shift?
In this case, yeah, we did a very nice, maybe you're talking about this one. So that depends on your design, right? If you can design it very well, you can make the transient go away. So initially that would be transient because you didn't initialize everything nice. But afterwards, if you be able to initialize afterwards, you can do that very nice. So it all depends on how you design the system and how you operate the system. You make the controller coordinated very well. So yes, this is a hardware design indeed. All right.
Okay, thank you. What's the main reason for weak grid oscillations? Is it design philosophy that leads to increase on VD increase, or is it a smaller PLL bandwidth?
Oh, that's the question of why you have weak grid oscillation. So there are lots of reasons that
Mhm.
we haven't talked about today here. So when we see this is become the system itself is very stressful, right? So you expect to see this if you have designed the voltage controller, the system has a limit. On the other hand, a lot of time you don't see very weak grid. So this weak grid that we show here is close to the operation limit. You expect to see. On the other hand, there are a lot of other things that we haven't talked about, right? For example, there's plant level control, there's delay. And once these are involved, then you will see lots of other weak grid issues that, yeah, probably something like this, something is growing up, but the grid is not that super weak. Still, it is a little bit weak, right? So you trip a line, you see oscillation coming in. So that they're like I said, their voltage, for example, voltage oscillation is very not popular as it's often seen, right? So those are things that once you do operation, people know how to fix that. They can tune controller, they can make adaptive gain, something like that, they can figure it out.
Okay. Is it wise to use robust PLL when grid voltage has harmonics along with weak grid conditions instead of totally replacing? Or is it possible to completely replace?
Uh-huh.
And the second question is, what is use of GFL in motor connected systems as they say we face issues with grid side converters?
Yeah, I probably forgot the second question, but let's first do the first one. Yeah, yeah,
The first one,
very good
is it
question. Yeah,
is it
yeah,
wise to use robust
yeah,
PLL
yeah,
when grid voltage has harmonics
yeah.
along with weak grid
Yeah,
conditions?
I like this type of questions from, I think, usually from academia graduate students, like a question. So first thing is about harmonics. So we haven't talked about harmonics, so that's a different topic that what is harmonic, what can cause it. The second thing is, why do you have to replace this? Can't you make it robust, right? So something like this. So for that one, we have to say it again. Yeah, maybe you design robust PL, you can improve certain limits, certain things, but can you still do something like what is called like a power based support, right? Something like greater level. So in addition, that's one thing that you when you change your point of view to do the grid operation, you ask yourself, it is having lots of changes. What about some like normal stuff that the power system guys operation are familiar with? For example, this one, remote fault is more vulnerable. Remote fault become more severe. That is completely against the lots of the paradigm that already been there for synchronous generator. So the philosophy, I believe, in the grid energy, it's not like you are wrong, you are wrong. It's just like how we can better operate the system as it is in the cheapest way. So using power-based, I think, stuff, the power-based synchron, probably trying to make sure that it can behave more like a synchronous generator. So again, it's not why you have to do this. It's just which one you put into the grid, it's cheapest. So when you have lots and lots of inverters, some of the battery you want to design this way. But again, lots of solar PV, you don't change it because maybe the original design is good for them. You just need to add a couple batteries to do grid forming. Yes. Let's go to the next question. Yeah. If we have time. Yeah, so I think Latoya, I missed you or I missed everybody.
Oh, here I
Oh,
am.
okay,
I'm so
okay. Yeah.
sorry. Are GFM, this will be our last question. Are GFM and GFL both capable of providing frequency support to the grid and participate in reserve markets?
Yeah, that's a very good question. This is some kind of power guys question, right? Yeah, GFL you can add additional FP tube. It can still provide um, frequency support. Yeah, if you are capable to design this way, and I think believe the industry may be quite something called a grid. They don't call it GFL, GFL. They don't want to differentiate it just by how you do synchronous. They don't care about internal stuff. They just care about can you provide grid functions as we designate. In the grid function you designate is basically can you provide frequency support? Can you provide voltage support? So if you can, you just call it advanced grid support inverter, something like this. So yeah, the short answer from here is yes, you can do that because you can just change the power reference and make it modulated by FP tube instead of the other one, the PF. That's it.